Hello, everyone. My name is Professor TK the Chemist, and welcome to the live that deals with colligative properties and intermolecular forces. We are going to go through several different examples today to show you all. Sorry, guys. Welcome to the live that deals with colligative properties and intermolecular forces. We are going to go through several different examples. Hold on, today got feedback. To show you all. Sorry, guys. Welcome to. All right, my bad, y'all, my bad. So we're going to go through colligative properties, and on this particular unit, we have several different formulas that you all will need to be aware of in order to be successful with colligative properties. If you guys have any questions at any time, please don't hesitate to put them in the comment box. I will be looking at the chat as we kind of go along today. So if you have questions, it may be on a little delay, but that's okay. We will still get your questions answered, if not during the live, but as a follow-up, okay? So what we have here today are some key formulas that you will need to know when it relates to colligative properties. So on this part of your screen here, you'll see the formulas that say essential formulas for intermolecular forces and colligative properties. The first thing that we're going to look at is the freezing point depression formula. The freezing point depression formula. Now, the basic formula is delta T of F equals the K of F times M times I. So I'm going to actually tell you all what each of those different letters and symbols represent. The delta T of F represents the freezing point depression, okay? It represents the freezing point depression. K of F represents the freezing point depression constant. The freezing point depression constant. Notice how we have different units for different parts of the formula. The first one where it says freezing point depression for delta T, we're talking about the temperature here, that's degrees Celsius. For the K of F, for the constant, that's degrees Celsius per molality. Now, you've probably heard of this word before, molality, which sounds similar to molarity, but there are two different processes or two different formulas. Molality deals with the mole of the solute divided by the kilograms of the solvent. Now, when I say the solute, we're talking about the thing that actually is the solid that's going to dissolve, okay? Then we also look at the solvent, which is the thing that's dissolving the solute. So in other words, if I have sugar and then I have water, sugar is the solute, water is a solvent. Then you also have the I, which is called the Van Hoff factor. Okay. And we'll delve a little deeper into that discussion also later on this morning or today, whenever you guys see this video. Now, the other formula that we're going to have to go through deals with the boiling point elevation, which is delta T of B equals the K of B times M times I. So again, this formula is quite similar to the freezing point, where with the freezing point, we were using K of F. In this case here, for the boiling point, we're using K of B, okay? But the formulas are identical. Just change the F for the B or the B for the F, depending on which one you're looking for. Now, the other formula that you will have to know about is osmotic pressure. The basic formula is, it looks like a pi, okay? The pi symbol that you guys have seen in math equals capital M, which is for molarity, times the R, which is a gas constant, times the T for temperature. Again, make note of those units, okay? Make note of the units that you will have to be a part of or know about when we go through these different examples. And then the other formula that you will have to know, molality. Molality. Now, you remember how I said molality sounds like molarity? Well, they do. They sound similar, but they're different in terms of the calculations. So when you're talking about molality without the R, molality's formula is M, the little funny shaped M, equals moles of solute divided by the kilograms of the solvent. And an alternative formula is M equals the mass of the solute divided by the molar mass divided by the mass of the solvent in kilograms. So in other words, when you look at the alternative formula here, you'll notice that the mass of the solute can easily be, I'm sorry, the moles of the solute can easily be converted to the moles by saying mass of the solute divided by the molar mass, depending on when you have to use that particular formula, okay? And then molarity. Molarity's formula is equal to moles of solutes divided by the liters of the solution. Okay? So those are your main formulas here that you'll have to know. I did mention something about the Van Hoff constant or the factor. We'll talk about this later on as we go through some of those different examples here. Hey, good morning. How are you doing? No, I got you. She means business. How are you doing today? So yes, we are over here now, doing our lives, as I had mentioned before while we were doing that. So we're trying to pull everybody here now since, TT doesn't know how to behave. Okay. So yes, we're over here. But thank you so much for joining me. Now, what we're going to do, we're going to go through our first problem here. I gave you all the formulas, but I'm going to give you all the examples on how to use them, okay? On how to use them. So let me go ahead and switch my screen out so you all can see how to solve these different types of problems, okay? So right here, I'm going to actually expand this to make it a little bit larger, okay? Make sure you guys can see that. So when we talk about the colligative properties, here are some examples here of how we actually can use them in the real life, okay? In the real world, okay? So I'm going to go ahead and make sure you got your calculators because we're going to need to use the calculators for our conversions here, okay? So I do have mine. So hopefully you all have yours. Okay, now as you guys are looking at these problems, and for those of you all that are on the replay, you can always go through the examples, pause the video before you see how we solve the solution so that you'll know how to do them as well, okay? So you can always pause the video before you see the solution. All right. So for this first problem, it says a nurse needs to prepare a dextrose solution for a diabetic patient. Calculate the freezing point of a 5% by mass dextrose solution. Given the K of F for water, which is equal to 1.86 degrees Celsius per molality. All right, so what is the first thing you think you should have to do in this problem? How would you go about solving this problem? Well, here's the thing. They give you in the problem the K of F, but what I'm going to do is give you the formula that we were talking about before, and we're going to see what part of this formula was actually provided for us in order to solve it, okay? So let me go ahead and go to my other screen to give you the formula that we're going to use for this particular part of the problem, because we're trying to calculate the freezing point. Okay. So I'm going to have you all plug in what you think you're going to need for this problem. Okay. So here we are right here. Okay. This is your formula right here. All right. This is the main formula. I'm going to actually highlight it so you guys can see that. Okay. Now, something that you all will need to know. In this problem, you can see given they gave you the K of F. So I'm going to highlight the other things that we were also given in the problem, okay? We were given the K of F. Now, something that you need to know. Whenever they give you this formula right here, okay, C6H12O6, you're going to have to find the molar mass of that in order to apply that problem. So I'm going to actually put that over here, okay? I'm going to plug that here, and I'm going to actually give you all the molar mass, okay? Because that's what's going to be associated with this part of the problem right here. the molar mass for dextrose, okay? So I'm going to give you that number also. Now, something else you need to know for this problem, okay? You need to also know that when you look at this example here, they're giving you, it says 5%. Now, when they say 5%, okay, what do you think you have to do in order to understand this whole process? Well, 5% has to be converted into uh, grams, okay? 5%. Because what they told you here is that you had let's go back through the problem again so that way you guys can see what I'm saying, okay? All right, you're going to calculate the freezing point of a 5% by mass dextrose solution. So the molar mass for this is 180. Oops. Okay. Grams per mole. All right. And in this case here, where they said the 5% by mass, we're going to actually take that 5% and say, okay, whenever you are given a problem of this nature, you have to assume that it's typically out of 100 whenever we see the percentages here. So we're going to say that that's 50 out of 100, okay? Whenever you see the 5%. So in this case right here, as a matter of fact, let me just write everything out, okay? So you all can see that. All right. So right here, you have to first calculate the molality because they did not give that to you, but what they did say it was 5%. All right. So I am going to take the 5% part of the solution. All right. And I'm going to say 50 divided by 950. Okay. In this particular case right here. All right. Now, before we go any further, who has had prior experience with molality problems? If you have, put a 1 in the comment box. I like to know what students have done prior, so that way I'll know, if I'm on the right track with you guys. For those of you all that need further clarity, in case this is all new to you. Okay, so put a 1 in the chat box if you are familiar with molality. If you're not familiar with it, put a 2 in the comment box. Okay, so here is the thing. Whenever they say 5%, the 5% means 5 grams of dextrose in a 100 gram of solution, okay? 5 grams of dextrose in a 100 gram solution. So let me again put that here. So anytime you see a percentage here, that means, let me just put that right here so you all will know, 5% means 5 grams in a 100 gram solution. Okay. That's the first thing that you have to know. All right. That's the first thing you have to know. So since we said 5 grams in 100 grams of solution, you're going to subtract those two numbers so that you can get the mass of the water. Okay. So again, you're going to take that 100 minus the 5, and you're going to get 95 grams. But you noticed here that the solvent has to be in kilograms, okay? The solvent has to be in kilograms. So I'm going to say 100 grams minus 5 grams. That equals to 95 grams, okay? That 95 grams has to be converted to kilograms. That's equal to the mass of water, okay? The 100 grams of solution is the water. The 5 grams is the solute. Now, because we know that we have to convert the 95 grams to a kilogram, what I'm going to do now, okay, is convert that number by simply either dividing by 1,000 or just moving your decimal back, okay, 3 places to the left, all right? So in this case right here, let me go ahead and scoot that down so you all can see that. I am going to take the 95 grams, convert that to a kilogram by simply moving my decimal, okay? Grams is in the middle, kilograms is 3 places to the left. 1, 2, 3, right there. So that gives me 0.095 kilograms of the solvent, okay? Remember, molality is equal to the moles of the solute divided by the kilograms of the solvent, okay? Now, we're going to move on to the next part of our step right here. Now, whenever you look at these problems, I want you guys to be mindful of the things that you have within your problem, okay? The 5 grams of the dextrose that we're going to convert to a mole is equal to, we're going to do it like this, okay? You're going to take that 5 grams. This is step number 2. You're going to take the 5 grams of the dextrose, which is C6H12O6, and you're going to convert that to a mole. So the 180.16 grams is on the bottom, okay? And on the very top is 1 mole. Now, we're going to get rid of course, our grams, okay, because we don't need those anymore. So we're going to say 5 divided by 180 0.16, okay? And you get 0.0278, okay? 0.0278 moles, okay, of dextrose. Now, what are you going to do with that number? Let me show you. You're going to take this number right here, okay? And you're going to take this number right here. And you're going to divide those two numbers because of our formula here for molality, okay? Remember, the formula for molality is equal to moles divided by kilograms. Now, rather than breaking that up into the multiple steps, we're going to go back to our formula up here, though, okay? So if you see this formula right here, I'm going to put a little check mark by it. That formula right there, we're going to say delta T of F equals to K of F times molality times the I. The I is the Van Hoff constant. Now, you're probably wondering, okay, well, wait a minute. What is the Van Hoff constant? How do I determine that? Well, because this is dextrose, there are some rules that you need to know. Whenever you have solutions like, or solutes like dextrose, okay, that's going to give you a different number here. The constant here would be 1, okay? Whenever you have things like sugar, we're going to actually have that equal to 1. So what you're going to do, and there are some other things we'll go along the way and have other problems that we'll do to show you different examples of how the Van Hoff constant gives you a different number depending on what that solute is, okay? So I'm going to rewrite the formula so you guys can actually see how to plug this in right here, okay? And that's equal to 1. So that way I'm just going to say 1, okay? Because this is a nonpolar solute also. That's the other reason why we're going to use that as our process here. So delta T of F is equal to K times the M times the Van Hoff constant, okay? Which is the I. So right here, if you remember up above, they gave us 1.86 and M per degree Celsius times. So right here, just so y'all can see, make sure y'all see that. Okay. Remember, this is the number that they gave us right here, the 1.86 degrees Celsius per molality. And then right here, to get the molality, I'm going to take the moles that we calculated earlier, 0.0278 moles over, okay, 0.095 kilograms, okay? And now I'm going to put a little note here. These two right here, the ones I'm highlighting, the moles and the kilograms, that's equal to molality, like that funny shaped M, okay? just FYI. And then times 1, okay? The Van Hoff constant right here that we told you about earlier. Now, the reason why I'm saying that is so that you know that the M's are going to cancel out, okay? The M's are going to cancel out because remember, you're trying to calculate your degrees, your temperature, your delta T, your freezing point. So you have to make sure that you're canceling those out. All right. So here it is again, 1.86 times 0.0278, and then divide that by 0.095, and we get 0.544 degrees Celsius. That is our answer for the first problem, okay? 0.544. Now, I'm going to let that problem breathe for a second, okay? I am going to let the problem breathe for a second. Now, when I say let it breathe, that means I'm going to let you look at it for a moment, think about it, and then we're going to actually move to problem number 2. But before we do, if you have any question, okay. And right, I see that the comments are coming through. They're delayed. So yes, you said 2, you don't have a clue. All right, I got you. So I'm gonna walk you through the next problem, and hopefully it'll make better sense for you. Sometimes when things are new, it's complicating. It's like, wait a minute, say it again, run that back again. I don't get it. Okay. So yes, I'm going to go through it again through another problem. Okay. So that way you all can see exactly how to do this. Okay. So one of the things I can tell you though is that whenever you are doing problems like this, you always want to make sure that you know what formula to use. And if you know what formula to use, then that's going to be very helpful for you when it comes to doing your calculations. Okay. So knowing what formula to use is very useful to know what formula you have to do for your calculations. Okay, so now let's go to number 2. And again, we're going to put all this, we're going to summarize it all up once we finish these problems. Okay, so here is number 2. Okay. All right, so this is number 2 right here. Okay. And let me go ahead and highlight this and make it a little bit bigger so you guys can see that right there. Okay. Right here, it says a blood preservation solution contains glycerol as a chiroprotectant. If a 12% by mass glycerol solution has a freezing point of negative 2.2 degrees Celsius, calculate the K of F of the solution. The molar mass of glycerol is 92.09 grams per mole. Okay, I got you. You say help me. I got you. Okay, one thing you need to know is the formula. Once again, we've got to use those formulas that we were talking about before, okay? And so if we go back, we know that delta T of F, because we're talking about the freezing point, is equal to the constant, K of F constant, times the molality times the Van Hoff constant, okay? Now, in this case right here, because we're dealing with another nonpolar solution, the Van Hoff constant is equal to 1, okay? I'm just going to go ahead and tell you that part right now. It's equal to 1. Now, what you're going to do, you're going to say, okay, let's see if we have everything we need to know in this problem. They're asking you to find the K of F. So what did they give us? They gave us the freezing point, which was negative 2.2 degrees Celsius. They told us that the molality indirectly was 12% by solution. So now, if we're going to rearrange this problem, we've got to isolate the K of F. So what I'm going to do is write this formula here off to the side so you'll know that the K of F is equal to the freezing point divided by M times I. The K of F is left by itself. But now something else you need to do. They told you 12%, right? Well, remember, that's the same thing as saying 12 grams, okay, of the solute in 100 grams of the solvent, okay, which in this case we know is water, okay? What you have to then do is say 100 minus 12 so that you can get the mass of the solvent, all right? I'm sorry, so that you can get the mass of the of what's left over in terms of the solution, because you have 12 grams of the solute, okay, which is in 100 grams of the solution. I should have said solution, not solvent, y'all. I'm sorry, my bad. Of the solution right here, because what we're going to do when we subtract those two numbers, we're going to get the number for the solvent. So imagine me taking 12 grams of a solute, pouring it in a 100-gram solution of something. Well, in order to know what that total is of the solution, okay, you have to take the 100 minus the 12, which is 88. So 88 grams is the solvent, okay? 88 grams is a solvent. Now, I'm putting all this pre-work in because as we go through the part of our problem where we have to find the molality, which is that little M right here, okay? That's equal to, once again, the grams of the solute, I'm sorry, the moles of your solute, okay? Divided by kilograms of your solvent. Now, here's what we've got to do though. We've got to convert, okay? I'm going to put this off to the side. You need to convert the 12 grams of the glycerol, which is what that was right there, okay, to moles. And they told you the molar mass right here, which was 92.09 grams, okay? So they told you that right there. So off to the side over here, we're going to do our math, okay? We're going to do our math for that part. So this is like a multi-step process, okay? That's the thing that many students get confused with, knowing which step to start with. So let me kind of pinpoint what you're doing here. That way you'll know exactly what to do, okay? Before I go any further, let me go back through this again. If they give you, anytime you see a percent number in the problem, it says 12% by mass glycerol solution. What you have to do is know that 12% means 12 grams of the solute in a 100-gram solution. You have to subtract those two numbers in this step right here, okay? You have to subtract 12 minus the 100, and the difference gives you the grams of the solvent. The 88 grams of the solvent is the water. The 12 grams is the solute, okay? So 12 grams is a solute, 88 grams is a solvent. Now, keep in mind that in order to apply the molality formula, okay, the part of the formula that we need to calculate molality, you have to convert the moles of the solute to, you have to convert the grams to the moles. So they gave us the molar mass of that, which was 92.09. Okay, so I'm going to say 12 grams, and because of space, I'm going to squeeze this in here, glycerol times 1 mole of glycerol divided by 92.09 grams of glycerol. All right, you're going to cancel out your grams here, and let's go ahead and divide that. 12 divided by 92.09 gives us 0.130, okay? 0.130 moles of glycerol. Now, we're going to plug this in right here on the very top. But something else we have to do too, we have to get the grams of the solvent into a kilogram. So if you remember, that's what we said before. You got to convert that. You're going to move your decimal place 3 places to the left. One. So let me put this off to the side so you all can see that over here. Okay. So you're going to take the 88 kilograms, 88 grams, and go 1, 2, 3. So you get 0.088 kilograms. All right. So you're going to use that part right there as we go through and use our problem, okay? So we're going to use our formula that we had up above. So again, don't get confused with these multi-steps. Just breathe in, breathe out, and look at what you have to do in order to solve the problem, okay? And I'm going to go back in and label it so you'll know which one was step 1, which one was step 2, okay? So right here, you're going to go back to that formula because remember, we're trying to solve for our K of F, okay? And this was the formula right here. I'm going to highlight it for you in green. This is the formula that we're going to use. K of F is equal to delta T of F divided by molality times the Van Hoff constant. Okay? Here on top of our formula is our freezing point, negative 2.2 degrees Celsius. So that number is going to go on the very top. So we're going to rewrite our formula and plug in the numbers that we need to solve this problem, okay? So right here, we're going to say K of F equals, and I'm just writing the formula back so you all will know where we're plugging in these numbers. Negative 2.2 degrees Celsius divided by, so on the very bottom, 0.130 moles per 0.88 kilograms, okay? And you know what, technically speaking, times 1. That's the Van Hoff constant. Technically speaking, guys, you can always find out what this is equal to so that you don't get confused in your calculator. So if I plug in 0.130 and divide that by 0.088, that's going to give us 1.48, okay? 1.48. So we can actually go ahead and take care of that without getting confused on the very bottom. So that's 1.48 molality. Again, times 1, okay? Which we know is going to still give us 1.48. So let's plug this in now. 2.2 divided by 1.48, and that's negative 2.2, that is, divided by 1.48, and we get 1.49. Okay. Negative 1.49 degrees Celsius per molality. That is your final answer for that particular problem right there. Okay. So I'm going to go back in and highlight our steps so you will know what step is what first. Okay. So here we are. Once again, I'm going to back it out so you all can see everything from top to bottom. Okay, in this problem, they told us we had a 12% by mass glycerol solution. They gave us the freezing point of negative 2.2 degrees Celsius. They also gave us the molar mass of glycerol. They want you to calculate the K of F. Well, we had to rearrange the formula to solve for that. So right here, okay, I'm going to put this right here in big bold letters right here so you can see that. This is step number 1 right here. Rearrange the formula, okay? Rearrange the formula. So the first thing is to get the formula. K of F equals delta T of F divided by M, which is the molality, times I. Step number 2 right here. They told us we had a 12% solution by mass. Whenever they say 12% by mass solution, that means 12 grams of the solute in 100 grams solution. But in order to find out, because the 100 grams is like your total, okay? That's your total amount of that solution. So it's almost like, just to give you a visual, you probably can't see because my background screen is maybe blocking it, but you have a salt poured into a liquid. We don't know how much this liquid is, but what we do know is it's a total of 100 grams. You take the 12 grams, pour it in, and then you got to figure out, well, how much liquid am I going to add? My solvent. Well, you have to subtract 12 minus 100, and that gives you 88. 88 grams of your solution poured in with 12 grams of the solute, and together you get 100 grams, okay? You have to then convert your grams of your solvent to kilograms. So that's step 3. Now, step 4 is to find your molality. Your molality is equal to the moles of the solute divided by the kilograms of the solvent. But in order to get your moles of the solute, you have to convert right here. This is step 5. 12 grams of glycerol to a mole because of the formula for molality, moles of the solute divided by the kilograms of your solvent. So 12 grams divided by the molar mass of 92.09 gives us 0.130 moles. So that number goes on the top. On the bottom, remember when we calculated or converted the grams of your solvent to kilograms? So we divided the 0.088 kilograms, that's on the bottom, with the 0.130 moles. And that gave us 1.48. And let me put the little funny shape M here so that you all will know that that's the unit for molality. We then took that and plugged it in to step 1's formula right here. And here is step 1's formula. Okay, so that you all can see that right there. You've got K of F equals delta T of F divided by the M for molality and the I, the Van Hoff constant. They gave us negative 2.2 degrees Celsius in our problem, and we went on ahead and calculated the molality here. For this step, we did that in step 4, right up there. So rather than plugging these numbers in here, getting you confused, we went on ahead and solved for that, which we got the 1.48, and that's the number that's on the very bottom. So 2.2 divided by 1.48, negative 2.2 that is, divided by 1.48 gives us negative 1.49 degrees Celsius per molality. I know that's a mouthful. I know that's a lot. I know it's a lot. That's why I'm letting you breathe. Breathe on that problem. Now, FYI, your constant will never be negative. So the negative sign actually drops off, and you're going to end up with, just simply put, 1.49, okay? So your K of F will never be negative. The negative sign will drop off. They were telling you that the temperature dropped to negative 2.2, but we will never have a negative sign for our K of F constant. So the constant is not going to be negative. So you're going to drop that off, and this is your final number right here. And if you were to go and look up these numbers in the back of a chart or a book, you will see that all the constants are going to have positive values, positive numbers. Okay, let's do another example. This one won't be as rough, okay? This one won't be as rough. So here is number 3. This is a forensic toxicology problem, okay? Something that some of you all may see in your field. And by the way, these are the type of examples that you will see on your TEAS exam. So for those of you all that are taking the TEAS exam for the nursing program, you do have to know about molality and solvents and solutions. Okay, so I'm going to go back again and I'm going to write out the formulas that we have used before, okay? This is the main formula right here, and this is dealing with boiling point. Okay, all right. So now, in this example here, it says a victim's blood shows an ethanol concentration of 0.15 molality. Calculate the boiling point elevation of the blood serum, given 0.52 degrees Celsius per molality. Okay, this problem is not going to be a lot. You know why? Because you don't have to do any calculations in terms of molality because they actually gave that to you. Now, in this example here also, what you want to know is that because you're working with, again, another nonpolar solution, your Van Hoff constant is going to be equal to 1, okay? So in this case right here, your I for Van Hoff constant is equal to 1. So now all we have to do is plug this in. The KB was 0.52 degrees Celsius per molality times 0.15 molality times 1. So all we have to do now is cross out the units we don't need anymore and just plug this into our calculator. 0.52 times 0.15 gives us 0.078. 0.078 degrees Celsius. And again, even if you multiply times 1, you're still going to have 0.078 degrees Celsius. Okay. And I'm sure a lot of students are saying, I want more problems like that on my test. Okay. More examples like this on your test. Okay. So remember, the boiling point formula and the freezing point formulas are the same. They are pretty much the same. Okay. Oh, and you know what? Let me go ahead and tell you this too. Since we're talking about the Van Hoff constant, I did mention I was going to explain to you all how you get the Van Hoff constant because they're not going to give these to you on your test. Let me go back over here and flip my screen so you can actually see this part here in terms of the Van Hoff constant, okay? So let me share this with you. Um, Hold on, let me make sure it was on. Okay, yes. So right here, these are some common values that you need to know, okay? So right here, as you can see, the Van Hoff constant means that if you have a non-electrolyte, like sugar or ethanol, your Van Hoff constant is going to be equal to 1, okay? Your little I is going to be equal to 1. But if you have something like sodium chloride, for instance, aka salt, okay? In this case right here, you have two elements, okay? And if you look at the subscripts, sodium and chlorine, 1 and 1 gives you 2. So that's how we get the Van Hoff constant equaling to 2. On the other hand, if I give you another formula like calcium chloride, okay, calcium chloride has a Van Hoff constant of 3. Why? Look at the formula for CaCl2. CaCl2. You have 1 calcium ion plus 2 chlorine ions, and that's how we get 3. If you look at the next formula, the next example here, you've got Al2 aluminum sulfate, SO4, 3. Well, if you look at the subscripts, again, you've got 2 aluminum ions plus 3. That, remember that 3 on the outside, not the 4. The 3 on the outside means you have 3 units of sulfate ions. So 2 plus 3 gives you 5. So that's how we're getting the Van Hoff constant. Oh, yes, 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 yes. Oh, you're welcome. No problem at all. No problem at all. And let's go ahead and practice some more examples. That way you can make sure that you know what we're talking about, okay? So, let's see here. Let me pull up some more examples. Okay. Just remember, you're looking at the formula. Remember, your non-electrolytes like sugar and ethanol, those deal with being equal to 1, okay? Those equal to 1. On the other hand, if I were to tell you that you add something else like an electrolyte, think about what you're going to give your patient to give them energy, so to speak, okay? So if you have a non-electrolyte like sugar or ethanol, those are non-electrolytes. But if you give them an electrolyte like salt, typically your salts are electrolytes. Those are how you're able to calculate it by looking at the formula, okay? By looking at the formula. Okay, so let me go ahead and give you some more examples, just to practice. Okay, let's see here. Okay, all right. Okay, so I'm gonna copy them over here so I don't have to keep switching my screen. Okay, and again, let's see right here. Okay, if I give you something like glucose, okay, glucose. Let me go back over here. Hold on, let me switch it off. Right here. Okay. Because this is glucose, the formula, like we said before, this is basically sugar water. This would be classified as a non-electrolyte. So therefore, you're going to say 1, okay? That will be equal to 1. Just FYI, that's equal to 1, okay? So just think, if it's an electrolyte, you're going to calculate it. If it's a non-electrolyte, you're not going to calculate it. Okay? You're not going to calculate it. Okay, let me give you another example. And I am mindful of the fact that some of you I may not know what an electrolyte is, and that's okay. But I will tell you most of the time, if it's something that you think you would actually give to a patient, okay, for health, that's kind of what you want to think about. But again, I know some of you all don't have of course, the expertise in knowing that right off the bat. But this is where you have to get into the polar versus non-polar bonds, all that good stuff that we talked about before at the very beginning of the semester. Okay. So if you know a polar bond versus a non-polar bond, that's how you're going to determine those different examples. So I'll do a separate video on this also to help you guys out with this so that you'll know exactly how to do them. So, as a matter of fact, I do have some on my YouTube channel already that you can actually go through and solve, okay? So I'm going to give you all these three to close out our session today on this topic right here, okay? So real quick, we're going to do these three examples, and then we'll be out of here. So we know that the first one was equal to 1, okay? Because that was a non-electrolyte, all right? These other three here are electrolytes. FYI, I'm just going to tell you, these are electrolytes. So therefore, let's calculate these. You've got 3 sodium ions plus 1 unit of the phosphate ion. So 3 plus 1 gives you 4. So the Van Hoff constant here will be 4. Okay. You have, for the next one, magnesium chloride. You've got 1 magnesium ion plus 2 chlorine ions. So 1 plus 2 gives you 3. Okay. All right. Now, in the next one, okay, in this next example, you always want to look at the ions of each individual element, and polyatomics, you keep them together. So again, when we say chemistry comes full circle, it's because of these examples right here. That's what we mean about the full circle moment. So in other words, if we look at ammonium right there in parentheses, that subscript on the outside is a 2 right there, okay? That subscript is a 2. And then you've got the polyatomic ion of SO4, but that's 1 unit of that, okay? That's 1 unit of that. So that's plus 1. So that gives you 3 right there, okay? All right. So I hope that this has been helpful. And again, sometimes when we look at things for the first time and we're not sure, it's always confusing until you go back and practice them again. Okay. So I will make sure to put these problems and more in my portal. So those of you all that want to be a part of the membership, you can get access to all these worksheets and practice problems so that you can go back through them on your own as well. All right. So if you guys have questions, make sure you all put them in the chat box, of course, so I can get your questions answered. And whatever the case may be, I hope you guys have a wonderful rest of your day. Take care, guys. And I appreciate you all for coming out and spending time with me today on these YouTube streets. Have a good one.